Okay, good afternoon. Welcome back to Drive's lecture. In the last class, we had said that we are going to look at the self-controlled synchronous motor drive starting mechanism because during starting condition, let me again redraw the structure of a self-controlled synchronous motor drive. So we are going to have a three-phase source side converter, which is a thyristorized converter on the supply side. This is going to work normally as a rectifier. So it is going to perform AC to DC conversion. So these are the six thyristors. And because it is a current source converter, we will have a large inductance on the DC side. And these are the three-phase power supply lines that are connected to the thyristor converter. So let us say this is VA, this is VB, and this is VC. And this is going to be three-phase 50 hertz supply from the grid. And we can say this works as a rectifier when we are looking at the power flow from the supply to the motor direction. And let me number these devices also. This is going to be T1, this is T3, this is T5, and this is going to be T4, T6, and T2. Now on the other side, again, I will have a three-phase thyristorized converter, but this is going to work as an inverter. That's what we said. So this is essentially the structure of the three-phase converter on the load side. So we can call this as motor side converter or load side converter. And sometimes because the load voltage commutates these converter devices, we also call this as load commutated current source inverter. So this is a load commutated current source inverter. And from here, we are going to connect this to the three phases of the synchronous motor drive. So here is our synchronous motor drive, and this motor may be connected or coupled to the load. And we already said that this particular converter, these devices, if I may call this as again A phase of the motor, and this is the B phase of the motor, and this is C phase of the motor. So we are going to call this as T11. Maybe this is T44. This is going to be T33, and this will be T55, and this will be T22, and this will be T66. Now, these devices are going to be fired exactly as per the speed of this particular synchronous machine. So whatever is the voltage that is available here at the terminal of the synchronous machine, this is going to be synchronizing voltage for the LCI. If I may call this as load commutated current source inverter as LCI. So this is going to be for the LCI devices. As I mentioned in the last class, we are not going to have a good amount of voltage for synchronization nor for commutating the outgoing devices of this converter. So we need to have a starting mechanism because of zero speed, no induced EMF in the motor. So there is no synchronizing voltage or commutating voltage. So this is not going to be available for this particular converter. So how do we start really the motor? So for that purpose, what we are looking at is something like this. Let us say this is my synchronous motor. And let us say I am drawing these windings in the form of concentrated winding. Probably this is going to be A and A dash. Although it will be distributed winding, but I'm showing it as though it is concentrated winding. And this is going to be B and this is going to be B dash. And this will be C and this is going to be C dash. So these are the three-phase windings. Now, clearly, from whatever we have got here, we should be able to say the positive current to the A phase will be carried, for example, probably by T11 and the return current will be carried by T11 and the forward current will be carried by T44 and so on. So, depending upon which two devices I have fired. For example, if I have fired initially, let us say T11 and T66. So T66 is B phase positive current and T11 is A phase return current. So this current is going to flow through T11 from A phase. So this is going to flow from A phase and then return through this. So that is going to be the current here. And if we are looking at um, T6, so that current is going to be somewhat like this. This is flowing through this and it is flowing through the B phase and then it is going to return through A phase and things like that. So when we have, let us say, A and B, both of them simultaneously conducting, and when we look at A phases MMF, A phases MMF will be somewhat like this if I am talking about forward direction, and B phases MMF will be exactly 120 degrees away. So it should be somewhat like this, and the third phase will be somewhat like this. This is the way it is going to be. So let us say this is FA, this is FB, and FC. So because of which, if I am looking at A phase positive and B phase negative, for example, both of them conducting simultaneously, so we are going to have B phase negative means it will be exactly in this direction. So when you look at the resultant of these two, this will be somewhat like this. This will be A positive and B negative. So which is, let us say, 6 and 1. So we are going to have an MMF somewhat like this. So if originally, let us say I had my motor's magnet somewhat like this. Let us say this is north and this is south. And maybe I'm going to have the magnetic axis now because of A plus and B minus somewhat somewhere here. So it will try to move towards this direction now. So the magnet will slightly move towards this direction. And if I want to make the magnet move further, maybe from 6, 1, I have to go to 1, 2, then 2, 3. So let me say 1, 1, 2, 2, then 2, 2, 3, 3, and 3, 3, 4, 4, and so on. This is how I will go sequentially so that the magnet moves from this position to the next position to the next position and so on. So for every switching, this particular rotor magnet should move by 60 degrees. So between these two, the movement will be 60 degrees. And again, between this and this, the movement will be 60 degrees. And between this and this, again, the movement will be 60 degrees and so on. But how do I know whether I have to switch over from 6 and 1 to 1 and 2. And when do I have to switch from 1 and 2 to 2 and 3? So for this, we will require initially a rotor position sensor. So the rotor position sensor will be very similar to what we spoke in terms of either encoder or resolver, which will actually be a mechanical position sensor, which is going to be attached to the shaft. So if this is the motor, let us say my motor is somewhere here, and I'm going to have a shaft. In this shaft itself, I will have a disc which is having some holes carved in the periphery, using which I should be able to find out what is the position at which the rotor is currently, what position currently the rotor is occupying. I should be able to say that. So what I need is a combination of rotor position sensor and some kind of commutation mechanism, because the voltage is also not there on the motor side. These devices, that is 1122 and so on, they have to be commutated at appropriate instant. Maybe they should be deprived of the current so that they are commutated properly. So we should have some kind of commutation mechanism put in place for this. So for this purpose, what we are going to do is, let us say we have fired this converter properly, because we have this supply side voltages which are very much present. Based on that, we are going to fire this converter for several cycles so that the current builds up in this inductance. Once the current builds up in the inductance, let us say I have first fired 6 and 1. I have fired these two. Once I fire these two, and if I know probably the rotor is originally occupying this position, it is going to start moving slowly. We always employ self-controlled synchronous motor drive for a very, very large capacity synchronous machine. So the inertia will be enormously high. So the movement will be very, very slow. So it can take maybe several seconds for the rotor even to traverse 60 degrees. So from the original position, it is going to move by these 60 degrees only very, very slowly. But the rotor position sensor will continuously send the signals out, from which we will know when this has almost occupied 60-degree position. So the moment it occupies 60-degree position, even if you give more and more current through 6 and 1, it is not going to move any further, because it has already aligned itself with the magnetic axis. So at that point, what we need to do is to stop giving the pulses to 6 and 1 now. And also, if you stop giving the pulses to 6 and 1, this particular inductor will not be able to give up the current. So because it will not be able to give up the current, we need to provide something like a freewheeling path. So we will normally have another thyristor connected, which is in parallel with this inductance, and that will be fired at the same time when you are stopping the pulses to T66 and T11, and you are going to stop the pulses to the rectifier devices, and you are going to release the pulse to this TD. So what will happen is, this current now will try to freewheel itself. The inductance stored energy will be dissipated, or it will be expended by circulating the current through this TD and this inductance itself, LD itself. And at the same time, because this is circulating the current right here, this particular converter will be devoid of any current. So this will not be able to supply any current to the synchronous motor. So no torque will be developed. So the rotor will actually be just, if at all it is moving, it will be moving only due to its own moment of inertia. And you are going to see that this converter also stops completely supplying any power to this, any current to this particular inductor. Now, after this has kind of, it is, that this current has almost come down to zero. At that point, you are going to release the pulses to the rectifier, allow the current to slowly build up. And simultaneously, previously, if you had fired 6 and 1, now you have to fire 1 and 2. So the sequence of operation is somewhat like this, based on the initial rotor position. Appropriate devices in the LCI are given pulses. What I mean is, if by chance the rotor had been occupying a position like this, maybe this is north and this is south, then correspondingly I might have to fire 2, 3 or 3, 4 or something like that. So I should know the initial rotor position. Based on the initial rotor position, we are going to fire 2 devices. So appropriate devices, that is 2 of them, have to be given pulses. At the same time, rectifier devices are fired in synchronization or in synchronism with the supply side voltage, which is 50 hertz voltage. So at this point, what happens is, thus current builds up in LD, which is the DC link inductance. So what you see is torque is developed in the synchronous machine and rotor starts moving. Now, once the rotor starts moving, when the rotor position sensor signals indicate that the rotor has moved by maybe 55 degrees or 60 degrees, close to 60 degrees. Then the pulses to LCI devices are withheld. So it is not going to be, fired anymore. And at this point, to deprive the synchronous machine or LCI devices of any current, the thyristor, the freewheeling thyristor, TD, will be fired simultaneously blocking the pulses to the rectifier devices. So both are going to happen simultaneously. These two are going to happen simultaneously. Now, At this point, you have essentially deprived any current to the synchronous machine by firing this and by blocking the pulses to this, as well as blocking the pulses to any of the devices in LCI. Now, all we need to check is whether the current has almost come down to zero. So we need to see once LD current is coming down to zero, rectifier is fired and the next two devices. So previously, if I had fired 6, 6 and 1, 1, then now I have to fire 1, 1 and 2, 2. So the next two devices in LCI need to be fired. So automatically TD would have gone off. This thyristor would have gone off once the inductance currents comes down to zero. So after this LD current is coming down to zero, TD will automatically turn off. Then we are going to release the pulses to the rectifier as per the synchronizing voltages, supply voltages VA, VB, and VC, and LCI devices, which are the two devices next in sequence. Those also need to be fired. Now, this is repeated until 10% of rated speed is reached and the induced EMF in the synchronous machine is perceivable. So once the motor voltage becomes perceivable, it has actually two major advantages. One is you are going to have a synchronizing voltage with respect to which you will be able to fire these devices. And the second thing is that there will be commutating voltage for each of these devices that is available. Because unless there is voltage on the AC side, which are going to change in their polarity from positive to negative and negative to positive, you are not going to be able to make sure that the outgoing devices of the load commutated current source inverter, they are turned off at correct instance. Okay. So the starting mechanism itself is a little complex, but it is done with the help of both the rectifier as well as inverter and the freewheeling thyristor, all of them getting pulses at appropriate instance. Okay. Now that we have understood the starting mechanism, let's start with the analysis of self-controlled synchronous motor drive. So, first of all, we can just represent the source side converter by a simple block. I'm not going to really elaborate on this much further because we all know this is going to work as a rectifier under normal circumstances. And if I call this as the firing angle as alpha S for the source side converter, it is going to be less than 90. So this is the source side converter. And this is going to be supplied with 3-phase 50 Hertz voltage. Now, from here, whatever comes out, it is going to be having the voltage has to be converted into a constant current with the help of an inductance, which is LD. And we are going to have this as the return path for the current. And here are the 6 devices. So let me again show the 6 devices clear. So these are the 6 devices what I have got. Now this is the DC link that is actually, connected here. And let me call this as probably the voltage VD1. And what is available here, let me call this as VD2. Okay. And I should have approximately VD1 equal to minus VD2. Very, very small difference between these two, depending upon how much is the current that is flowing and how much is the drop that is taking place in the resistance associated with this inductance LD. Now, let me draw the three-phase uh, uh, lines that are going to the synchronous machine here. So, depending upon what is the speed, I should say, if I say this is VA, this is VB, and this is VC. So, VA or VB or VC, the magnitude as well as the frequency depends upon the speed of the synchronous machine's rotor. Okay. And depending upon the speed, because the frequency is decided, the firing of these devices, if I may call this as T44, this is T11, this is T66, and this is T22, this is T55, and this is T33. All of them are going to be fired exactly in synchronism or in synchronization with the speed or the frequency. So if I am looking at the voltages that are VA, VB, VC here, somewhat like this. So with respect to omega t, if I may say that this is, let us say VA, and I'm going to divide this into 60-degree intervals like this. So I can draw VB somewhat like this. And I can draw VC somewhat like this. So these are going to be the three-phase voltages what I am looking at. Okay. Now, let us say initially I am having maybe 6 and 1 conducting. So let us say this is VA, this is VB, and this is VC. And under this condition, if I try to again draw what is the kind of voltage I am getting, basically at the terminals of the synchronous machine, from this VD2, whatever I have as the voltage here and what is happening in the other side. And please remember, this is working as an inverter. It is not going to work as a rectifier. So if I am looking at, for example, inverter means alpha L, the load side converter firing angle has to be greater than 90. So in all probability, if I say this is the natural point of conduction for T11, because this is VAC 0 crossing. So this is alpha equal to 0, alpha L equal to 0 degree. So from here I have to calculate. So this will be alpha L equal to 30. This will be 30 plus 60, 90. So I have to have somewhere here. Beyond this only I have to fire. So let us say I am firing at, this is 90, 90 plus 60, 150. So let us say this is alpha L equal to 150 degrees. This is where I'm going to fire 1. And I'm going to fire 2 at this point and 3 at this point. And I have to have rest of the devices also fired in the same way. So we said 1 is fired at this point. So 2 is going to be fired at this point, 3 is going to be fired at this point, 4 at this point, 5 at this point, and 6 at this point. This is the way it is going to be fired. So when 1 is fired and 6 and 1 are simultaneously conducting, I'm going to get VAB as the voltage. So A is here and B is here. So let me draw VAB zero crossing is somewhere here. This is where VAB zero crossing is. So VAB is going to be somewhat like this. So this is 90. So the peak will be somewhere here and it will come down like this. This is going to be VAB. So when I am firing one here, I may get a voltage basically somewhat like this coming out. And it will continue until normally 2 is conducting. This is how it is going to be. Okay. And if I try to look at after that, it will be VAC. So VAC again will be from here, there will be a jump. And I have to have VAC probably, where is VAC? VA and VC. So this is where VAC zero crossing is. This is where VAC zero crossing is. So VAC would have risen like this, and then it would be going around like this. So it will be again going like this. And, after that again, I will have, so this would have been the kind of waveform I should have had. So before that also, I should show as though this would have been the previous one, this would have been the previous one, and so on. So something like this. This would have been the waveform, somewhat I should have got. So this is VAB when 6 and 1 are conducting. This will be VAC, and this is 1 and 2 are conducting. Then 2 and 3 are conducting, which will be VBC, and 3 and 4 are conducting, which will be VBA, and 4 and 5 are conducting, which will be VCA, and 5 and 6 are conducting, which is VCB. So this is the way it should have been. This is the kind of voltage I should be getting across this. And please remember, VD2, what we are looking at is actually it will have plus here and minus here. The other way around, because you are looking at alpha greater than 90, which means the DC link voltage itself is going to be 3 Vm divided by pi cos alpha. And alpha being greater than 90, you are going to get this to be a negative voltage. So if I say this is VD2, because alpha is greater than 90, VD2 will be with a reverse polarity. So that is the reason why we get plus here and minus here, which is indicating the reverse polarity. Now, the synchronous machine normally has a large excess value. The synchronous reactance is going to be pretty large. So that is as good as having source side inductance. If there is source side inductance, we already said that when you are firing 1, 5 is not going to give up the current right away. Otherwise, what you would have seen is the A phase current would be exactly something like this. And it will abruptly come down to 0 and it will remain at 0 for the next 60 degrees. And when 4 is fired, you're going to have the current exactly in the opposite sense. Again, we are drawing this current with respect to rectifier. You have to think about the current in exactly the opposite way. So if I try to draw the A phase current, I will have actually positive current until here, and a zero current interval and a negative current here. This is the way it is going to work. So this is when 1 is conducting along with 6 and this is 1 conducting along with 2. whereas here 4 conducting along with 3 and 4 conducting along with 5. So this is the way it is going to show the current. This is the A phase current if I had not had any source inductance effect. Because I have the source inductance, fairly large, because the synchronous reactance of the synchronous machine is pretty large. When I am actually giving the pulse to 1, 5 is not going to give up the current. So there will be a current flowing actually from C phase as well as A phase. A phase current will be slowly increasing. C phase current will be slowly decreasing at the same rate. So we are going to have actually the current here, it will slowly increase like this. And it will reach this peak. And when you're trying to wear off 1 from conduction and 3 is being fired, then also it will give up the current slowly. So the current will look somewhat like a trapezium. The same way, when you are looking at 3 and 4, when the 4 is fired, 2 will not give up the current so easily. It is going to go up like this, and again 4 will not give up the current right away. So during this portion, we are going to have both 4, 6 and 5, all of them conducting. Similarly, during this portion, we are going to have 5, 6 and 1, all of them conducting. So this is what is going to happen. And this interval, we call it as commutation overlap, mu. So this mu depends upon multiple things. So the commutation overlap, it depends upon multiple things. Let us try to analyze this a little bit. So under this condition, what is going to happen is we are going to have, first of all, I'm talking about this particular interval. So we are going to have the current flowing through 6. So we are going to have the current flowing through 6, T66. And it is going to flow into the B phase. And it is going to return through 2 phases. So I'm going to have Z A, and I'm going to have Z C. So I will have one inductance here like this, and one thyristor like this, another thyristor like this. So this is the way it is going to be. And it is going to ultimately return to together to the DC link. So these two ultimately are going to connect together and the DC side. So what is flowing here is, let us say, ID. What is returning here is also ID, which is a fairly constant value because of the inductance. In fact, rather than showing this as ZA, ZB, and ZC, let me show this as the synchronous reactance corresponding to B phase. This is the synchronous reactance corresponding to, let us say, let me call this as T11, and let me call this as T55. So this is going to be ZC or LLC, and this is going to be LB, and this is going to be LA. And I will have the induced EMF here. This is all will also be the induced EMF. This will also be the induced EMF. So this is going to be the circuit which is corresponding to this commutation overlap interval here. Now this is VB, and this is VA, and this is going to be VC. And what we have drawn here are VA, VB, VC, as you can visualize from the waveforms, what we have drawn here. Now, what is going to happen is, if I look at the current through this as I1 and this is I5, I should say I1 plus I5 equal to ID. And I know that I5 is slowly giving out the current and I1 is taking in the current. So I1 is increasing and I5 is decreasing. And ID, which is same as I6, this is a constant. So I am going to have essentially dI1 divided by dt, that is going to be equal to minus dI5 by dt. That is, rate of reduction of current in device number 5 is going to be equal to rate of increase in the current in device number 1. This is how it is going to be. Now, I should be able to say VA and whatever is the drop here. So I should say VA, and this current is increasing. So I should say minus LSD I1 divided by dt should be equal to VC plus LSD I5 divided by dt. Because I am looking at from this point onwards until this point, what is the total voltage difference? I have written that basically. So VA minus LSDI1 by dt is the voltage that is existing between this point and this point. The same way I have written what is the voltage existing between these 2 points. So I should be able to say that VAC should be equal to 2LS dI1 by dt or dI5 by dt. So whatever is the drop in the inductance, whether it is here or here, that will be equal to VAC divided by 2. So when I look at what is the voltage that is coming across the DC link, or the DC terminals between these two. This is the DC voltage, which is VD2. So this voltage is VD2. So VD2 originally would have been whatever is VA and VB, the difference between these two. That's what we drew as VAB here. The difference between these two would have been the voltage across the DC link. But now, because this inductance is also taking up some drop, what I get as the output is going to be only VB minus whatever is the difference between these two. So it is going to be decreased by a factor of VAC by 2. So the reduction in the DC voltage is going to be whatever is the voltage VB originally minus the drop in the voltage. So whatever we had was VAB, let us say VAB would have been the original voltage minus whatever is the drop in the inductance, LS. So I am going to have basically whatever is the drop in the inductance, that is going to be LS multiplied by DI by dt, so which will be VAC by 2. So we will have a reduction definitely corresponding to, so the reduction is going to be something like VAC divided by 2. This is going to be the reduction in the DC voltage. So what happens during this particular portion is, instead of having VAB, we will have actually, if you look at it, VCB would have actually gone down further like this. Okay, it would have gone down like this. So it will be an average between whatever is VAB and VCB. So if VCB is this and this is VAB, during some portion, what is going to happen is rather than getting VAB, we would get a little lesser voltage and it will jump to VAB. So it will be somewhat like this. This is VCB and you are going to have something, it would have suddenly jumped to VAB. Rather than that, it is actually going to see that it is somewhere in the middle, then it jumps to VAB. So this portion, what I have got as the difference, this is going to be the drop in the DC voltage. So similar thing is going to happen at every 60 degrees. So after this, it jumps like this. It should have actually taken over right away from here, but it is going to just come as the average between these two. Then it will again jump and things like that. So it will repeatedly go through this. So this portion, what I have got every time, that is going to be the drop in the DC voltage. So this drop in the DC voltage happens because of the commutation overlap, and the commutation overlap is going to impact multiple things. One is because I am not going to be able to allow the outgoing device. If I say that I am firing T11, at that point the outgoing device is T55. So T55 will not turn off immediately. As it is, if you look at it, for T55 to turn off, if I want T55 to turn off, I should have a reverse bias across this T55. And for getting a reverse bias across T55, this is VC. And if T11 is conducting, this will be like a dead short circuit. So VA will come here. So I should have VAC to be positive. Only until VAC is positive, VAC is positive, T55 will go away. Only if VAC is positive, T55 will be reverse biased. Otherwise, T55 will not be reverse biased and it will not go off. So first and foremost thing, even after T55 gives up the current completely, it should be reverse biased at least for some duration. So there are two factors involved here. One is if T55 gives up the current only after mu only after mu duration, commutation overlap duration of T11's firing. Then possibly T55 can go off. So T55 can go off only after a duration of mu, even after T11's firing. Second thing is, after T55's current goes to 0, it has to be reverse biased for a duration equal to omega TQ, where TQ is the turn of time of this device, which is given in the data sheet normally. And it depends upon what is the speed at which the motor is rotating. This omega is the speed at which the motor is rotating, and TQ is the turn of time of the device. So VAC has to remain positive to reverse bias this device T55. So T55 will be reverse biased only if VAC is positive. This we already wrote. VAC, only if VAC is positive, T55 will be reverse biased. So if you really look at it, this is alpha L equal to 0. This is the point at which alpha L equal to 0. So VAC will remain negative or positive only until this point. So this is VLC zero crossing. So normally you can say alpha L maximum is 180 because after that VAC will not be positive. Only if VAC is positive, T55 will go off. It will be reverse biased. So alpha L maximum theoretically is 180 degrees. But if I want finite duration, which is corresponding to omega TQ, I have to have 180 minus this omega TQ. So that is what will allow T55 to be reverse bias. So let us say I'm going to have a margin for this particular T55 to go off. That means, let us say gamma is the margin angle, which has to be greater than omega TQ. It has to be greater than omega TQ. Only if it is greater than omega TQ, then we are going to be able to turn it off. So this is the duration for which VAC will remain positive. After T1 is fired. So we are going to say that if theoretically we can fire it even at alpha L max equal to 180 degrees, I have to hold off by at least an angle gamma. So alpha L max minus gamma is the firing angle, which should be the maximum firing angle practically. But not only this, I have to take care of how long it is going to take for my device to give up the current. That also I have to take care of. So if I call this angle as mu, I should say alpha L max minus commutation overlap angle mu minus gamma should be the actual maximum firing angle. I cannot go for any firing angle greater than this. Otherwise, I cannot ensure the outgoing device will be, kind of turned off and the incoming device will successfully turn on. I will not be able to ensure that at all. And it will be a dead short circuit eventually. So I essentially need to ensure that beta is the angle at which the maximum firing angle at which the load commutator converter LCI can operate. And this should be calculated as whatever is alpha L max, which is theoretically 180 degrees, minus mu minus gamma, where gamma is slightly greater than omega TQ. Maybe I can write gamma is twice or thrice omega TQ, where omega is the speed of synchronous motor drive. And TQ is turn off time. TQ is going to be the turn off time of T66 or T11 or whatever, T55. All of them will be similar. Now, mu is going to be commutation overlap angle, and mu heavily depends upon the commutation overlap angle Mu is the commutation overlap angle. And it heavily depends upon multiple things. One is, what is the speed at which? So it is going to be proportional to speed of the operation of synchronous machine, because omega times whatever is the time duration t, that is going to determine the angle. So definitely omega makes a lot of difference. Then it is also going to depend upon what is the current that is being carried, or indirectly torque value at which the machine is operating, or the power value at which the machine is operating. And the third one is, what is the value of XS or LS, the inductance of the synchronous machine itself. All these three things determine exactly how the commutation overlap, what kind of value comes up during the operation of synchronous machine. So in general, when you analyze the synchronous machine and when you determine what could be the maximum firing angle for the load commutated inverter for the self-controlled synchronous machine, you are going to look at multiple things. One is, what is the speed at which you want to operate your machine? What is the maximum speed? And what is the rated torque at which you are going to operate the machine, and what is the inherent value of this inductance. Based on that, you will determine what is the amount of commutation lead you have to give. So this is generally known as the commutation lead angle. Beta is generally known as the commutation lead angle. The firing angle is 180 degrees minus mu minus gamma. And commutation lead angle, we call this as the commutation lead angle. How much of lead you are giving really for allowing the commutation to take place. So this is determined based on what is the maximum speed you want to operate the machine in, what is the maximum torque or rated torque, and what is the inherent synchronous inductance of this particular machine. So if you really look at it, ultimately, the control loop for the self-controlled synchronous motor drive is somewhat going to be like this. If I want to achieve a particular speed, reference speed, I'll have to definitely compare it with the actual speed. And this will go through a speed controller. And this speed controller indirectly will decide what is the kind of torque you require or current you require. So you are going to require, let us say, you determine what is the current. And this current has to be adjusted such that you are going to have the DC link current compared with this. So let us say this is ID star and this is going to be ID actual. So let us say I have a rectifier here and I have an LCI here. And I'm going to have, let us say, here is the inductance and here is the DC link current I am looking at. So this is going to go like this. This is the DC link current. Now, what comes out of here is going to go as the control circuit for source side converter. So this is going to be the source side converter. So it is, let us say this is source side converter. Let me call this as SSC. Now from here, this controller is going to give the firing signals to this. Now this is the three-phase supply what I have got. So this is three-phase supply, what I have given here. Now from here, the output is actually going to my synchronous machine. Now from the synchronous machine, I am going to have a rotor position sensor or EMF sensor, terminal EMF sensor. So that is essentially going to tell me which devices I have to fire initially. And if I have EMF, automatically that will be going as the synchronizing voltage. So from this, I should be able to get the speed as well. It's not a big deal. So I should be able to get the speed as well. Now, from here, from the EMF value as well as from the rotor position sensor value, I will have the firing circuit for the load side converter or load commutated inverter. So this is the load side converter. And this firing is going to go to this based on all the input. And one more input I may require is what is the beta value. So what is the safest firing angle value at which I'll fire it? In fact, depending upon whatever is the voltage, you might decide even the beta value accordingly. So this is the way generally the control is going to be done. And please note that the synchronization is automatically done with the rotor EMF. So that is the reason why there is no independent variable for LCI control. So that frequency is not an independent variable in this particular case. That is one reason why hunting oscillations are always eliminated in an LCI fed drive. So load commutated inverter fed synchronous motor drives are always used in such applications where you just cannot tolerate any hunting oscillation. Only one point that I had missed, which I would like to just emphasize, is we already drew the current somewhat like this. We said that the current is going to be, A phase current is going to be somewhat like this. This is the way the current is going to be. So if I say that this is where I'll be able to fire the A phase device first, that is alpha equal to 0, but we are always talking about alpha greater than 90, and alpha is always less than, much less than 180 degrees, because you have to give a margin of both mu as well as gamma. We already talked about this. So we cannot really fire it at 180 degrees. It has to be definitely much less than 180, it may be 150 or 160 or something like that. So the current is always going to be somewhat like this. The current, what you get for this particular device will be probably starting somewhere here. So it is going to be starting somewhere here and then going around like this. That is how it is going to be. So compared to just a second. Let me again draw this clearly. So this is A phase voltage. So this is what is the A phase voltage we drew. So this is what is the A phase voltage we drew. So if I try to look at the current is somewhat like this. This is the current that we had drawn for A phase for a firing angle of 150 degrees. And because it is a discontinuous current, please look at this. This is the current it is starting. Otherwise, it would have been a rectangular current. So if it had been a rectangular current, let's say this is the A phase voltage. And for alpha equal to 150, we showed as though we should have had the current somewhat like this. It would have gone to 0 here, and 60 degrees it is keeping mum, and then it is going to be like this. If it had been a rectangular current, this is how it would have been. So if I try to draw the fundamentals middle point will be somewhere here. Here also it will be fundamentals point. So I would have had a current somewhat like this. This is how the current would have been. If it had been even a rectangular current, it would have gone off like this. So which means you are going to have this current leading the voltage. This is the voltage. So current will lead the voltage in an LCI. So we should always have a little bit of over excitation as far as the rotor is concerned. Only then you will have a leading power factor. So the LCI fed drive, because it works at an alpha which is greater than 90 but less than 180. We are going to have always the current leading the voltage by a factor of some alpha minus mu by 2. So we have to have the synchronous machine in over-excited condition. That means the field current has to be somewhat supplied extra. That's what I was trying to say. So now let us try to do one numerical example on self-controlled synchronous motor drive. So let me try to, first of all, give the statement of the problem. So the problem statement is going as follows. 1,000 kilowatt, three-phase, 6.6 kilovolt, 50 hertz, 6-pole, UPF, unity power factor, Y connected or star connected, synchronous motor drive, has XS equal to 30 ohms and RA equal to 0. Assume that commutation overlap can be neglected. This motor is controlled by an LCI. When LCI works as an inverter, alpha L is 150 degrees. During braking, when it functions as a rectifier, alpha L equal to 0 degree. Calculate the supply side converter firing angle for the following conditions. One, motor operates delivering rated torque at 750 RPM. 2, motor operates in braking mode at 750 RPM at rated torque. Assume that motor operates at constant voltage to frequency ratio and resistance associated with the DC link inductance LD is 0.2 ohm. So let's try to work out the solution for this problem. Let's first calculate the rated current. So rated current. Another thing I think we need to say is supply side voltage is 6.6 kilovolt. Supply side converter input voltage equal to 6.6 kV. So now the rated current we can calculate here, that is 1000 kilowatt, which is 1000 multiplied by 10 power 6 divided by root 3 VL and PF. Power factor is unity, so I can simply put 6600. So this comes out to be 87.5 ampere. This is the rated current. So whenever we are talking about rated torque, hopefully we should assume that the motor draws rated current. Now, looking at the speed, we should be able to say the frequency has to be correspondingly lower. If it is a 6-pole machine, synchronous speed is 1000 RPM. that is 120 F by P, which is 120 multiplied by 50 divided by P, which is 6. So that comes out to be 1000 RPM. So at 750 RPM, frequency should be equal to 750 multiplied by 50 divided by 1000. So this comes out to be 37.5 hertz. So this comes out to be 37.5 hertz. So if it is a 6.6 kilovolt machine, I should say for 37.5 hertz, terminal line voltage, that should be 50 multiplied by, rather 37.5 multiplied by 6,600. That should be the terminal line voltage. Okay. So that comes out to be 4950 volts. And we know originally from our three-phase converter expressions. So for a three-phase converter, per phase RMS current will be root of 2 divided by 3 ID, where ID equal to DC side current. This is one expression we had derived earlier in converter fed DC motor drive. One more thing we have to say is 3 Vm divided by pi cos alpha will be the DC side voltage. So we can calculate what is the DC side voltage for this converter, and it is already given that if it is working as an inverter, it is going to have alpha L equal to 150. And the first condition is motoring operation. So inverter LCI should work as an inverter with alpha L equal to 150. So I can write this as 3 Vm is the peak line voltage. So I should say root 2 times 4950 volts. This I have substituted here, divided by pi cos of 150. This will be the DC voltage. Obviously, it will be a negative voltage, but you should also remember when we are looking at the voltage, if we say this is plus and this is minus here, here it is going to be reverse. So still it will be plus and minus here, but what we get will be with the negative sign because alpha is greater than 90 degrees. So here, if you calculate, you are going to get a negative value of voltage, and that voltage comes out to be 5787.2 volts. So this is 5787.2 volts with the negative sign. Now, this is the voltage at this point. This is going to be 5787.2 volts. Now, we have to add whatever is the drop in this, and that will come out to be what is the DC voltage. And once we have the DC voltage, we should be able to calculate what is the firing angle for the source side converter because we know the supply voltage as well. So I can say if it is rated torque, our current is going to be 87.5 ampere. So I should say I RMS per phase is 87.5 ampere at rated torque. So ID is going to be root of 3 divided by 2 I RMS. I'm just using this expression. So that comes out to be, what is ID? That comes out to be 107.14 ampere. So once we calculate this, we can say ID times RD, where RD is this resistance associated with the inductance. So let me call this as RD. So RD is 0.2 ohms according to this. So that is going to be 107.14 multiplied by 0.2 volts. So now I can say VD on the rectifier side is going to be 5787.2 plus ID RD. Okay, so that is DC. So let me call this as VDC. Now VDC will be equal to 3 Vm divided by pi cos alpha S, where Vm is going to be 6,600 times root 2 divided by pi cos alpha S. So from this equation, we should be able to calculate alpha S, and alpha S comes out to be 49.3 degrees. So this is the source side converter firing angle when we are looking at the machine operating at 750 RPM and rated torque, neglecting commutation overlap. Now, if we are looking at the second condition where it is in braking mode and 750 RPM at rated torque. So in braking mode, what is going to happen is, this is the synchronous machine we are talking about. And these are the three phases. And we have this as the LCI. Now this is going to work as, if it is working in braking mode, this is going to work as a rectifier. And if this is working as a rectifier, and I am going to have now this as plus and this as minus, now we are going to have the current still flowing like this. This current will still flow like this, but we have to add whatever is the drop in this RD. Rather than adding, we have to subtract, and then we have to see what is the value of the voltage at this point. So if I say this is VD2 and this is going to be VD1, so I should say VD2 minus IDRD is going to be equal to VD1. That is going to be the actual equation during braking. And this is VD1, and we are going to have, this was originally working as a rectifier when we looked at this as a motor. Now it is braking operation, because of which this is going to work as an inverter. And we have to assume that because it is an inverter, alpha S will be greater than 90, whereas here alpha L will be equal to 0, because according to the problem statement, if it is working as a rectifier, alpha L is 0. So this is going to be 0. Now this is going to be connected to 6,600 volts, 3-phase, 50 hertz. So let us go with the calculation, whatever we had made. The terminal voltage, what we calculated, will still remain the same because V by F ratio is a constant. So 4950 volts is going to remain as the terminal voltage. This will be still 4950 volts. Now, only thing is we have to calculate IDRD, which will be again similar to the IDRD we calculated because it is still rated torque condition. And rated torque condition, we calculated the current on the DC link. The current on the AC side does not change on the motor side, but DC link current will also not change because we are using the same value here, and DC link current comes out to be 107.14. So we are going to have 107.14 multiplied by 0.2. This is going to be the DC link current. So we can say 4950 was the terminal voltage. 3 Vm divided by pi cos 0 degree. That is VD2. That is going to be equal to 34950 times root 2 divided by pi. This is going to be the DC side voltage VD2. So that comes out to be 6682.5. Now, from this, we have to subtract IDRD. So I should say 6682.5 minus 107.14 multiplied by 0.2. This will come out to be VD1. Once we calculate VD1, we should say again 3 Vm divided by pi multiplied by cos alpha s. That is going to be equal to minus VD1 because this is working as an inverter. So with plus here and minus here. So this is essentially minus VD1. So this is going to be 3 multiplied by 6600 times root 2 divided by pi cos alpha s, from which we should be able to calculate alpha s, and alpha s comes out to be 138.4 degrees. Please remember, we have actually neglected the commutation overlap as well as turn off time. That is because already in a safe way, the load commutated converter's firing angle has been taken as 150 degrees, which will give 30 degrees of margin between 180 and 150. There is a 30-degree margin which should take care of the commutation overlap as well as gamma, which is margin angle, which is giving a margin for commutation. That will be at least twice or thrice omega TQ. So, in synchronous motor drive, just to summarize, in synchronous motor drive, what we discussed as topics, various topics. We basically looked at types of synchronous motors. So we talked about a wound field rotor, in which we said there could be cylindrical or salient pole. Then the second type we talked about as permanent magnet rotor. In that also we said it could be surface mounted or interior permanent magnet machine. And the third one we talked about as reluctance rotor, which does not have permanent magnet or windings. So this is a very simple and rugged structure, but only thing is it will require field excitation current also drawn from the stator side. That is the disadvantage. So this will always be at lagging power factor. After this, we basically talked about working of synchronous motor drive. We talked about equivalent circuit, phasor diagram for both cylindrical pole and salient pole rotors. We talked about power angle relationship. We talked about hunting oscillations. We also discussed V and inverted V curves. Then we came over to braking operation. So this was only dynamic braking, nothing else, where we will only connect three-phase resistance on the stator side and we will leave the excitation as it is. And beyond that, we discussed about speed control. So in speed control, we talked about true synchronous mode where the frequency could be an independent variable and hunting oscillations will be visualized. And the other one is self-controlled mode. So this kind of brings us to the end of synchronous motor drive. We have not really looked at field-oriented control or direct torque control of synchronous motor drive, especially pertaining to PMSM. If time permits, we will look at it at the end. But the next topic that we are going to discuss is special machines. So we will be looking at permanent magnet brushless DC motors, stepper motor, and switched reluctance motor in the next class.